Hello, 8th graders. This is the video for potential and kinetic energy conversions. This is the next ELR after you have already practiced making the calculations for these two things. Now we're going to talk about how they interact with each other. So in this video, we're going to go back to our roller coaster that we actually started with in the first couple of ELRs, and we are going to define the law of conservation of energy. So this is something that probably looks very familiar because it is similar to stuff we've done in chemistry. So energy can't be created or destroyed, it can only be transformed. In other words, potential energy can turn into kinetic, and kinetic can turn into potential, and back and forth, but the total amount of energy is always going to stay the same. So if you look at the little roller coaster, you'll notice that potential energy is going up and down, kinetic is too, but the total is always staying the same. Now, one little side note, this is only true for friction-free environments, which, as you probably can guess, are just a thing that happened in textbooks and not real life. But to be fair, friction is only when energy is being turned into heat. And heat is a form of kinetic energy, so I mean, technically the energy is being conserved and all of 100% of it is still there, but we can't see it in the motion of the object anymore. So we're going to be dealing in theoretical world for our practice problems, and we're going to ignore friction for our practice, but you should know that it is a big component of these kinds of questions. So now that you've got those blanks filled in on your worksheet, let's talk about how we actually do some calculations. Let's say that we've got this guy on a skateboard and he's about to go down this jump, and each little 10-meter mark along the way has been labeled. He has a 45 kilogram mass. Here are the kinds of things that we can solve. We're going to figure out how much kinetic energy he has down at the bottom of the ramp. We're going to figure out how fast he is going at just a random spot. We could do this for any spot. I just picked 15. And finally, we're going to figure out where is he on the ramp when he has 25 meters per second worth of velocity. When he's going that fast, where is he? These are the three things we're going to be able to solve, and then you're going to get some practice at the end. So let's start off with how much kinetic energy he has down at the bottom. On your paper, you'll notice that you have a place to write down the steps, show your work, and a final answer. Well, let's talk through the logic of this first. Those are the steps. So according to what we just said, if we look at the potential and kinetic energy, it's always going to be a total amount of whatever he has at the beginning. Well, here's the thing. A lot of times you're going to be tempted to start with kinetic energy. You're going to be like, oh, how much kinetic energy? I can solve for that. Well, if you solve for kinetic energy, look at what you would have to do. Kinetic energy equals 1/2 mv squared. We know his mass, but we don't know how fast he's going down at the bottom. So you won't be able to solve if you start with this purple equation. So sad day, we have to try something else. Well, we know that all of his potential energy at the top, as he's up here at the top of the ramp, all of that is going to be turned into kinetic when he gets to the bottom of the ramp, because he won't have any height anymore. That energy had to go somewhere, and you can't destroy energy, so it had to be turned into kinetic. So if we can figure out what his potential is at the top, we know that that has to be the kinetic down at the bottom. So that's what this says. That's what you have to summarize in your steps. All right, so we've got to start with potential energy. We know that equation, mass times gravity times height. We have all of those details. We know he's 45 kilograms. Gravity on this planet is 10, and he's starting at the 40-meter mark, so we can find his potential energy, and that works out to 18,000 joules. Therefore, when he gets to the bottom of the ramp, he's going to have 18,000 joules of kinetic energy down here at the very bottom. Okay, so we've now solved the easy of the three. Let's go to the middle one. So now we want to figure out how fast is he going at some spot on the ramp. So I chose 15 meters, but again, you could choose any spot. You can do this for any spot on the ramp. So let's talk about the logic. How are we going to do this? Let's think it through. Well, we know that his total energy from the last question is 18,000 joules. Everywhere on the ramp, whether he's here, 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 any spot, even when he goes back up the other side, every spot along the way, he's got 18,000 joules, because energy cannot be created or destroyed in our friction-free pretend world. So because of that, we can find his potential energy at this spot and do some subtracting. So if we know that his total energy is 18,000, and we can figure out what his potential energy when he's lower down on the ramp, it's going to be a lower number. And the difference is going to be whatever his kinetic energy was. So like that missing amount when he goes down the ramp, that had to be converted into kinetic. And then we can plug that back into the purple equation, and we'll get our answer. So let's go through those steps. So we're going to start with his potential energy. And we know that he has 45 kilograms mass, gravity on Earth is 10, and we're talking about the potential energy at this random spot right here on the ramp. He's at 15 meters at that spot. So his potential energy, when he gets down to where the arrow is going to be 6,750. Well, if his original starting amount of energy was 18,000, now his potential has been dropped to this 6,750 amount, the difference has to be his kinetic energy, because all that amount had to turn into something. It had to get turned into kinetic. So his kinetic energy is quite large, 11,250. Okay, so in other words, at this arrow, he's got two types of energy going on. He's got potential and he's got kinetic. Here are those two amounts. If you add them together, it's his total still. He hasn't lost any total energy. He's just been turning it into kinetic. Okay, now we have a kinetic amount. We know his mass. Now we can use the purple equation. So we go back to purple, plug in the stuff that we know. You're going to do 1/2 times 45. Then you're going to get your number in your calculator. You have to divide that into 11,250. And then you have to do the square root. Once you've done all that stuff, you'll get V is equal to 22.36 meters per second. So that's how fast he's going at this arrow. And we could do that for any spot on the ramp. Okay, now the last one. Now we're going to figure out where is he on the ramp, or how high up is he when he's going 25 meters per second. We don't know where he is, but we want to find that spot. Let's talk the logic again. Well, again, we know his total energy everywhere on the ramp is 18,000 the whole time. Because of that, we can find out what his kinetic energy will be when he's going 25 meters per second. And whatever the difference is, because we know it's always got to be 18,000, whatever the difference is between these two numbers has to be his potential. And then once we have that, it'll show us where he is on the ramp, because once we know his potential energy, that's another way of getting us to his height. So let's start off with kinetic this time. Let's figure out how much kinetic energy he has if he's going 25 meters per second. I'm going to plug in the stuff that we know, do our squaring first. Don't forget to square first. When you do that, you're going to get his kinetic energy to be a little over 14,000. So that means that 18,000, his total everywhere on the ramp, minus his 14,062.5, that has to tell us what his potential is going to be. When we do that math, we find out his potential is a little under 4,000. Okay, now we can go back to the green. If we know his potential, we know his mass, and we know gravity, now we can solve for his height and figure out where he is on that ramp. So, green equation, we're going to go plug in all the numbers that we know, do 45 times 10, then divide that number into 3,937.5, and we will get our height to be 8.75 meters. So he's going to be somewhere either here as he's going down, or when he comes back up the other side, he could be here also, but he's in one of those two spots. All right, now that you've seen and taken notes on 2 or 3 different questions, now it's your turn. For the practice, I need you to go onto the back side of your paper and work out these 3. Number 3 is more of a written answer. I want to know your written thoughts, so you obviously don't need to show any math work on that one. But all of the answers for these practice questions should be checked at the front counter when you are done. Good luck.